Hello, we are Group 1 and Team 1 of the MECH 2409 project design. We're doing the monoski frame, and my name is Miriam. My teammates are Mohanad Shabaka, Harris Iqbal, and David Mendez. Today we will explain our final design of the monoski, the dimensions, and explaining two conditions that were used while testing. So what's a monoski? A monoski is basically a ski that's used by Paralympics. It consists of a chair on top, a frame in the middle, and a single ski in the bottom. It helps those who have some sort of disabilities to enjoy the sport of skiing without worrying about the functioning of a normal ski or a snowboard. As you can see from our final design, our design has a simple idea of using a connector in the middle with shafts that can move in or out according to the movement of the person on the ski. There are also springs connected from the bottom base to the connector that was in the middle. These assist further in moving and providing the needed pull. When choosing the material for our design, we focused on mass and stiffness. We wanted to reduce the overall weight of the monoski while keeping its maximum strength. This is to endure the forces that are applied to the frame and the springs. We chose to choose high-strength aluminum. This is for the shafts and the connectors, as well as the top and bottom base. And we also picked stainless steel wire for the springs. These materials were seen as the best choice for the simulation on SolidWorks. Since there weren't many dimensions available for us online from previous designs, and there weren't many differences in them, we chose to stick with the minimum and the maximums that were available online. And our design has a minimum height of the frame of 50 centimeters, and it can expand according to the movement up to 85 centimeters. So basically, the base has a width of 27 centimeters and has a length of 126.62 centimeters. And that's also the distance from like one end of the shaft to the other. For the connectors, the distance between one connector to the other is 15 centimeters. And the diameter of them is 12.73 centimeters. These choices were selected by us according to the materials that we used and giving the best results that we can get during the stimuli. Every other dimensions using the ski and all of that was done based on the actual monoski designs that were available online. And you can preview other dimensions of the monoski on this slide and take a closer look into how big or small some parts are.
When attempting to do an element stress or deformation analysis on the previously shown model of the frame, we ran into a number of problems due to its complexity. Therefore, a new but similar frame was made with the same shape and dimensions of the original one, but with much simpler connections to make it possible to conduct a finite element analysis for the monoski frame. The first loading condition used in our analysis of the frame was the static loading condition, where a force of 700 newtons was simulated as an applied vertical and lateral load on the top plate to represent gravity and the weight of a person using the monoskis. In the figures, you can see the fatigue infinite life cycle analysis and the fatigue damage percentage diagrams of the frame as a result of the static load analysis.
For the second loading condition, we chose to analyze cyclic loading. Forces with magnitude of 700 newtons were used again to simulate an average human weight, and the gravity acting on the monoski was also included. The results obtained by the SolidWorks analysis are shown in the following image. The ultimate results of the FEM analysis indicate that under cyclic loading with the applied loads mentioned, the design should theoretically have an infinite life, due to the fact that the von Mises stresses are way below the yield criteria for the material and the design layout. In the safety factor analysis, similar loads were used. We decided to analyze the factors for every major component in the monoski. The results given by SolidWorks were the following. The shafts, with a safety factor of 2.3, are definitely not a concern. Here are the results for the bases, which have a factor of 2.4, also not bad. And the middle piece with a safety factor of 14, which is extremely high. Finally, the holders, which is the only concern we have. As we can see, the safety factor is way below 1, which is a dangerous feature that we do not want in our design. For this reason, we have decided to remove the holders and instead attach the shafts directly to the bases, without any intermediate connectors. This should not make any drastic changes to the design, as its structure remains intact, but it will solve the safety factor issue of the holders.